Sup, kids? Let's get this party started. Question 23. Oh, you guys are talking about question 23. All right. So, let's talk. Let's go straight into this. All right. So, on Monday, was it Monday? Yeah, on Monday, you guys didn't necessarily like how I went about doing it. So, I'll tell you what I'm going to do is I'm just going to pull out the equation we finally derived at the end of Monday, put it straight up on the board, and let's talk about it. Let's kind of go about it the way I don't necessarily like going about things, as far as like, here we go. Let's memorize this equation. A equals P times 1 plus, what was it, 1 plus I over N to the NT. Cool? Write that sucker down. A equals P plus 1, or times 1 plus I over N to the NT. And this talks about your compound interest formula. Got it? All right. Yeah, all right, fine. Let me just show you what this formula is, how to use it. It's pretty simple stuff. The A is your final amount. And usually what we're talking about here is money because it's compound interest, but it doesn't necessarily need to be money at all. It could be like the final amount of monkeys that you have, the final amount of bacteria that you have. It's just, I don't want to just say it's the final amount of money. It's the final amount of anything that you're talking about and applying this equation to. We cool? Whereas P is your principal. Amount. So Sophia likes to say this is your y-intercept, and we've had discussions about it, and eventually I end up agreeing with her. And yeah, essentially, this is how much you start with. This is how much you put in at time equals 0. Cool. Now, the I is your interest. Okay? The I is your interest. And it's like if you, and it's usually talking about like your interest on how much the growth or decay is as far as like annually. And annually means once per year. So if you put this in an interest rate that incurs 5% every year, then you would put 5% in there. You guys got it? All right. The N, this is the number of times you are evaluating. Per T. All right, so this is the number of times that you are evaluating per time. Okay? And what I mean by time is T doesn't necessarily need to be 1 year exactly. T can be anything. It's just the letter T. If I wanted it only to be a year, I would change it out for a Y instead. Maybe not a Y. Y is usually reserved for the vertical axis or anything, but it's per amount of time. So in this case, usually time is 1 year, so how many times are you evaluating this interest per year? Does that make sense? All right. To answer your question, Lucas, if it's a 5% growth, then yes, I would agree with your statement where this stuff in the parentheses would be 1.05. If, of course, n is equal to 1. Right? And what I'm saying there is that, like, if I am doing 5% annually and I'm only evaluating this once a year, then yes, I'm going to take my principal and multiply it by 1.05, and I'd be good. But if I were doing it twice a year, then I would take my principal and multiply it by 1.025. Because if I gave you 1.05 and I did it twice a year, I'd basically be giving you 5% and 5% in that same year. You know what I mean? Yeah. We'll get there. All I'm doing. Is giving you the equation uh, and showing you where each piece comes from. On Monday, I basically broke it down for you, and then we ended up arriving at this equation. So today, what I'm going to do is I pulled it out of my butt, throw it up on the board, say memorize this, and then I told you, hey, let me show you where each piece comes from. And I think that maybe the discussion I just had was a little bit confusing. I said something like 5% annually with n equals to 1. If you put your money inside of an account that I evaluate the interest only one time in that year, and I give you 5% of your money, then what you would do is you would do 1.05, as Luke has suggested. Does that make sense? This stuff in the parentheses would end up being 1.05, because you would take I would give you 100% of what you put in there plus an extra 5%. Okay? Now, if I told you I'm going to evaluate this thing twice a year, so I'm going to wait 6 months, evaluate it, and 6 months and evaluate it again, and I'll give you interest on both of those days. Got it? Then what you would say is, okay, I wouldn't use 1.05 in that parentheses. What I would use is 1 plus 5%, which is 0.05, divided by 2. Right, which is where I got the 1.025 from. Does that make sense? Because if I gave you 1.05%, it's almost like if I'm giving you twice the amount that I should. So what I need to do is, if I'm evaluating it more times, then what I'm going to do is if I'm evaluating it more times, what I'm going to do is I'm going to not give you as high of a percentage based off how many times I evaluate it. But yes, you're right. You're right, exactly. That's only the stuff inside the parentheses. You also have the to the nt. So then the n over here is 2. So you're going to square it as well. So we discovered that in the end, the more times you evaluate it over the year is actually better for you. And yeah, it only made a difference of 13 cents in our like $100 thing. You know, you get 13 cents more. But hey, man, 13 cents is 13 cents. I mean, if you think about it, like if you invest $1 million, you're going to have a difference of like $450. I'll take $450. You know what I mean? I have no problem with saying, hey, I want $450. I think that you'd be crazy, or at least maybe, I don't know, maybe you're not as poor as me, but if you're like, nah, $450, I'd rather just invest once a year. I'd rather you evaluate it only one time a year as opposed to every day. You know what I mean? All right. Are we cool with that? Does that kind of make sense to you? So I think that one of the problems that we have here is, okay, wait. There's one more piece. There's one more piece. Where does this 1 come from? That number 1 over there. That number 1 stands for the original amount, right? Because if the amount of money you get out is equal to the principal times this, that means I stole, instead of having like I gave you 5% more money than you originally had, If it didn't have that 1 there, it would be like, hey, put in your $100. I'm going to steal $95 from you. You know what I mean? And you guys be like, that's jacked up. Well, you guys didn't tell me to put in the 1. You didn't want me to put in the 1. The 1 is 100% of your original investment. Okay, and the T, what is the T? That's your time. Usually it's measured in years, but we could say, oh, it's any interval of time. For money, we're going to stick with it being years, like as measured in years. For bacteria, that might not be the case because bacteria grows way faster than money. I mean, it depends on what kind of things you're investing in, of course, but I'm just saying. Bacteria grows uber quickly, so you probably don't want your time to be in intervals of years as opposed to maybe minutes. You know what I mean? So you would adjust this equation accordingly. Anyway, this equation isn't magic. We didn't pull it out of our butts and throw it up on the board, say memorize everything in there. It all makes sense. Here's the breakdown of how it all goes. We cool? All right, let's try one of the problems. Let's do something is evaluated 12% annually versus 11.3% annual interest rate compounded monthly. Cool? So which would give you more in a single year? So all we do is we'd say, all right, well, in this case, n is equal to 1 because I'm only evaluating it one time in the year. It's evaluated 12% annually, one time annually. In that year, I've only done it once. So I would just plug that into my equation. I get P times 1 plus 12%, which is 0.12, divided by the number 1, times 1 to the 1 power, or n times t, so that's 1 times 1. We cool? So then you just plugged it in. All right. For this one, you plug these numbers into your equation. It's P times 1 plus 0.113 divided by 12 to the 12th power times 1. So then all you do is you plug this into your calculator and this into your calculator and see which number is bigger. Which number is bigger? I don't know. Let's see. So that's, is it 1 plus 0.113 divided by 12 to the 12th power? Oh, on this side, I end up getting that all of this junk is equal to 1.119. Cool? And all of this junk, well, that's pretty easy. It's just 1.12. So which number is bigger? The first one. That's all you do. Now, some of you guys are freaking out because I didn't give you what P is. I didn't tell you, oh, P is equal to, 100 or whatever. Well, obviously, if we're comparing the two side by side, P is going to be the same number. So whether or not this is P times 1.12 and the same P times 1.119, this one's going to be bigger. Because you're multiplying that same P by a bigger number, you'll end up getting a bigger stuff. And yes, Sophia, you're absolutely right. Only by a little. They're different only by like a very small amount. Okay, all right, fine, fair. But what if this were $1 billion? What if P was $1 billion? You know what I mean? So I'm going to multiply 1.112 or 1.12 times a billion. That would be 1, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay? And then this one over here, I'll multiply that by a billion. That's 1, 1, 1, 9, 1, 2, 3, 4, 5, 6. All right. So that is a difference of $1 million. I'd rather have the one that has $1 million. You see what I mean? And when we're talking not necessarily about money, but maybe bacteria, these numbers P can get super big. So I have no problem with saying that this is going to be, this could, you know, I mean, it does make a difference, even though this number is very small compared to that number. I mean, the difference between this number and that number is so manini. Yes, but when you apply it to gigantic numbers, like the number of atoms, huge numbers, these differences make a difference. We cool? All right. So, you guys think you guys get that? Is that homework pretty easy? All right, let's see. What is it that I really want to get to? Okay, this might be good. All right, let's try one of these. How much? Here's a question from your homework. I believe this is from your homework. Let's try it out. How much is $1,000 invested at 8% annually worth? Okay, wait, here, we'll do part 2 of this question. How much is $1,000 invested? So your principal is $1,000. Got it? And then your annual interest rate, so I is equal to 7.8%, also known as 0.078 number. And then compounded daily, so n is equal to, what is n if I said it's compounded daily? 365, cool. All right, 365, and then it's going to happen over 20 years. So t is equal to 20. Yes, and you're right, Lucas, technically you want to evaluate this to be 365.25 if you want to get super technical. Yeah, you're right. I would just stick with 365. You know. Yeah. All right. All you would do is this. I ask you, what is A? Oh, shoot, that's easy. A is equal to 1,000 times 1 plus 0.078 divided by 365 times 365 times 20. All I did was I plugged all these numbers into that equation up there, calculated it out, and that's my answer. What do you mean it's out of 1,000? What are you talking about? It's out of 1,000. No. My principal was 1,000, so the P is out front, so I just put 1,000 out front. Oh, no. It's not 0.078%. It's 7.8% is equal to 0.078 in terms of numbers. Because you can't plug a percentage into your math equation. You have to change it to a number, right? So you just take this 0.78 and you move the decimal place 2 times to the left. 1, 2 gives you 0.078. Yeah? Yeah, it's 7.8%, or at least it's question number 2. See, it's compounded 7.8% right there. Daily. So, that's what it is. We cool? All right. Let's look at this. Let's do this. I want to introduce you to something that I think is rad. Can I erase this? Let's see. Okay, all right, I'm going to do this. I'm going to give you the answer ahead of time, and then I'm going to show you where we get it. I'm going to try Sophia's technique out. So write this down. I'm going to put a squiggly line here. I'm going to put a dot, dot, dot. E, squiggly equal sign, 2.71828, dot, dot, dot. That's just like writing, what is the squiggly equal sign, you might ask? Well, it's just like writing pi is equal to 3.14. But we know it's not equal to 3.14. It's 3.1415. In fact, we know it's not even that because it's an irrational number. And there's millions of people who can say pi out to 100 digits or whatever, right? So I can say, oh, it keeps on going and forever and ever and ever. But so technically it's not exactly equal to that number. So I'm just going to put a squiggly equal sign, which means it's about there. You know what I mean? And I'll put a dot, dot, dot to say, continue on with the measurements of, or the digits of pi, depending on how nerdy you are. Cool? Well, E is this new number. And we're wondering, what is this new number? Where did it come from? Why do we have it? Okay, all right. So E is called the exponential growth, or the exponential factor, okay? And it's so important that we have a letter for it. Just like pi, it's one of those numbers that appear when you least expect it. It's kind of crazy. Yeah, this is going to be the beginning of logarithms, and logarithms can be really crazy for people, and so I wanted to talk about E and what that is. All right? Let me show you. Yeah, well, we got to move on. All right. Let me show you where it comes from. Okay? An important factor inside that equation that I just showed you is this thing right here. 1 plus I over n to the n. Cool? All right, it sounds like you guys are all freaking out. I'll tell you what, before the end of class, yes, we will go back to Bradley's questions. But I want to at least introduce to you E. Sound fair? All right. This thing right here was really interesting to us. If we want to turn it into the equation we just had, then I would put a p out in here and I would raise this whole part to the t power. But I'm getting rid of those things because I'm interested in this part right here. Cool? Now, if I made I equal to the number 1, what does that mean? Think about that. If I is equal to, there we go, our interest is 100%. So that means if you put this inside of my bank account and I told you interest is 100% and you put in $10, the next time I evaluate this, how much money are you going to make? How much money are you going to have? You're going to have $20. So it's kind of this doubling thing that happens, right? Well, it's because if I is 100%, then I'm telling you, give me your money, and in 1 year, I'll give you 100% of it in addition to how much you gave me. So basically, so you look at me and say, oh, so basically you're doubling it, right? And I'd be like, yeah, basically I'm doubling this. Okay? So I'm interested in the equation that we had before, just that middle part that was really interesting, and I'm interested when I equals 1, where we have this doubling effect. So we've got this 1 year, 2 years, 3 years. So say I start off with this amount of money right here, and then after 1 year, I'm going to evaluate it immediately. And it's going to double. Like that. Cool? And then after another year, I evaluate it immediately. And that's going to double. Are we cool? No, it's not going to double. It's going to double what you have in here. So if you put 10 bucks here, you're going to have 20 bucks here. You're going to have 40 bucks here. And you'll have 80 here. Are we cool? All right. Now, this is really cool, but I hate to say this. This isn't how the world operates in money, in biology, in anything. I mean, it's not necessarily how things go, right? Like, think about it in terms of biology, okay? Let's think about it in terms of biology. Say that you have a cell. All right? Good. I'm glad you asked that question. Why? Why should I care, and why doesn't this happen in the real world? Sorry, Sophia. I'm sorry you have to go. You can go if you want. I'm going to try to finish this off in about 10, 15 minutes, but I would like to make sure I answer Bradley's questions. But I really want to get to this stuff. So I'll make sure to upload this thing by the end of school day. All right, here's what I'm saying. You have a cell, and it goes through, what is it? It's called meiosis, right? Right? Bradley, you're good at this stuff. No, is it mitosis or meiosis? Mitosis is the one that has it makes the sex gametes. Okay, all right. You're right. Sorry, it's mitosis. You got a cell, and it's going through mitosis. So after, it's not going to take a year. I don't know how long it takes. Maybe, let's say, after 1 hour. Say that the cell duplicates itself after 1 hour. So after 1 hour, you'll have 2 cells. And after 2 hours, you'll have 4 cells. Does that make sense? Okay. But here's the problem is, does that mean at a half an hour, like in between here, I'm only going to have exactly 1 cell? And then at 11 or at 59 seconds and 99/100ths of a second, I'm going to have exactly 1 cell. And at 59 minutes and 59 seconds, I'm only going to have 1 cell. And then exactly at 60 minutes, I will have, boom, 2 cells magically appear. No. Would you agree with me in saying that? Would you agree with me in saying that at half an hour, you'll probably have 1.5 cells, right? Yeah. That would be a more um, that would be a more accurate statement completely. Yeah, it doesn't duplicate, like let's say it duplicates every hour, but it doesn't do exactly a duplication on the hour. It doesn't go like this. One cell, one cell, one cell, two cells, two cells, two cells, two cells, four cells. You know what I mean? This is what we call a step function, and that doesn't happen in this thing, right? But rather, it's a gradual growth that kind of looks like that, right? So what happens is, in this section right here, you'll have your one cell, but you'll also have this extra bit of cell appearing. And then over here, you'll have your one cell and that extra bit of cell appearing, but you also have an extra bit of cell that is appearing because it has a little bit more to work off of. You see what I mean? So what we're doing, yeah, that's exactly how it works. That makes sense to me. It doesn't go boom, boom, boom. It kind of gradually grows, right? It's like if you put in $100 here, and I evaluate this thing maybe every second, okay? Then in the middle of the year, like I'm going to evaluate this thing off the previous second, but I'm going to evaluate this thing based off of your original amount plus all the extra interest you made. And then that grows up just a little bit more, so I'm going to evaluate that even more to evaluate that to be your original amount plus the extra interest you made. You see what I'm getting at here? So if I wanted to emulate real life, like biology, which, you know, maybe this compound interest isn't important to you in terms of money, even though money does behave exactly like this. But maybe it has something to do with like biology or chemistry or physics or any other science. Then what would be really interesting to me is if I made n to be a really big number. Sound good? Because the bigger n gets, like if it's 1, then I do it annually. If it's 2, I'll do it biannually. If it's 12, I'm going to do it monthly. If it's 365, then I'm going to do it every day. If it's 525,600, then I'm going to do it every minute. Yes, I know how many minutes are in a year, right off the top of my head. Okay. So if n gets really big, that's going to emulate life very accurately. Sound good? So here, I'm going to make a table for you. And I'm going to show you something. Here's my table. Here's n, and here's the results. If n is equal to 1, then I'll take 1 plus 1 divided by 1, so that's 2, to the 1 power, so your result is going to be 2. Are we cool? If n is equal to 10, then your result is going to be 2.59374,246. ... I did all this stuff in the calculator beforehand. But all you do is you just take 10 and plug it in here and take 10 and plug it in there. We cool? Nothing complicated. Just, you don't even need to write down all these numbers. I'm just trying to prove a point. If n is equal to 1,000, then your answer is going to be 2.7169239. No, this isn't a percent. This is how many times you're evaluating it. So this would be like if we were to evaluate 100% interest one time a year, you would get twice the amount back. Whereas if we were to evaluate this thing at 100% interest 10 times a year, n equals 10, you would get 2.5% back. If we did 1,000, you would get 2.7169% back. So I think that the really curious thing here, the really interesting thing here is, as I get n to be a bigger number, this number gets bigger. Is it going to get bigger till it gets to 3? Can I make it 3? Can I make this number 3? All right, let's check it out. If n is 100,000, then your answer is going to be 2.718268237 ... And if n is 1,000,000, no, let's make it, if n is 10 million, here's what your answer is going to be. 2.7182826 ... Do you see something happening here? Okay, why doesn't it get as huge? No, it is getting bigger. It's getting bigger. But it's not getting bigger as fast. The reason why it's getting bigger is because we're bringing it to a bigger exponent, right? And when you bring a number that's bigger than 1 to a bigger exponent, that answer is going to get bigger. But the other factor that's happening here is this divide by n. Right. This divide by n isn't making the number that you're bringing to a bigger exponent bigger. It's actually making that number smaller. So these effects are kind of canceling each other out. And as n gets to infinity, your answer for this thing is e. That's what e is. E is the number that's inside the parentheses that emulates continuous growth. And that's how the world works. So that's where e comes from. Now, do you have to do anything like this stuff in your math homework? No, not really. I don't even know, how did your teacher introduce pi to you? They just said, use it because it works? It's really important. Learn this stuff. Here's a number. Whenever I write pi up on the board, immediately you think brainwash 3.14. Yeah, okay. Well, that's the same with e. I'm not going to do that thing where immediately when I write e up on the board, you should immediately think, oh, okay, well, 2.71, all of that kind of stuff. In fact, to be honest with you, I don't know very many people who actually memorize this number, 2.71828. And the reason why they don't memorize this number is because it's on your calculator. See this button right here above ln? E to the x? That's all we use it. I mean, that's all we need for using it. I don't ever plug in the actual e. I just have the calculator do it for me. Any calculator you have, whether it's your iPhone, whether it's your, this thing, unless of course it only has 10 buttons on it, it has an e. There's a pi too as well, so you don't actually have to memorize pi to any digits. Are we cool? So what do you think? Was that interesting? Was that crazy? I mean, it wasn't magic. It really wasn't. All I did was I plugged in n for bigger and bigger numbers, and I'm finding that it does get bigger, but it doesn't get bigger as fast. In fact, wait for it. I don't want to blow your mind or anything, but I just went through an advanced calculus lesson with you. That's what calculus is it's thinking about numbers as they grow and how it affects certain things. And we looked at this and said, as n gets bigger, this number over here is going to get smaller, so that percent increase is going to get smaller, but you're doing it more times. So this is kind of what's going on. That's exactly where it comes from. All right. I'll tell you what I'll do. I am not going to have time to go over Bradley's questions with you, and Bradley's going to be upset with me, and I know he does, and I know he's often upset with me. So, Bradley, I want you to email me, and I know that you guys often email me and I don't respond, but I want you to email me your questions, and I will make a special video just for you and the rest of the class tomorrow answering those homework problems and whatnot. I'll try to upload it as soon as I can, but I think that today's lesson was actually a pretty good one, and I didn't want to speed it up or slow down or whatever. All right. But I will say this. Bradley, you're going to have to study biology pretty heavy if you are going to be an anesthesiologist. I feel like this stuff right here, this E stuff, is going to be something that might be of interest to you, because it's talking about exponential growth or exponential decay. And anytime you interface math with biology, you're going to find E somewhere in it. I guarantee it. I think that's fascinating that this number appears. It's a compound interest thing, but it appears in biology because it applies to life. That's crazy. In fact, any science like physics, chemistry, we all use this E value. I think chemists don't use it as much. But physicists and biologists and mathematicians, they all use E. That's like one of their favorite numbers. All right, anyway, talk to you guys later. Have fun. See you on Friday. Shoots, brah, pow.